Hi, I'm finally back from California and I haven't made a video for a couple days, so I'm a little bit, I might be behind you or I don't know. I don't know where you are. You might be working on the test right now. The last, there's just a little bit left in the class, but I think the last really major thing is doing some type of statistical application now that we understand probability a little bit better. And some of the things we did with the central limit theorem really leads us nicely into this section. We tried to fit in a statistical application just because some of the departments that require the probability class want their students to see some type of statistics in the course, and this I think probably is the most relevant given what we've already built up so far in the class. So here's a nice comic. Obviously we got to start with that. So let's come down a little bit. So I'm just going to define a little bit about statistics, a little bit of background, and then I want to build a confidence interval. So statistics is a discipline concerned with, this is a big word, optimal acquisition of data. This is not an easy task, getting good data, good random data representative of your population. If you take in bad data, your results are not going to be worthy of even displaying. So optimally acquiring data and then analyzing it in order to model some type of situation. And a lot of probability, we use those probability models to model a population to make predictions about the future. Statistics has two branches. If you were to take 223 or an AP Stat course, part of it is just doing descriptive statistics. This just means you collect a set of data. So maybe I'm collecting data on GPAs of Rose-Hulman students. So let's say I take a random sample of 10 students and here's some of their GPAs. I'm just making up numbers. I don't know. I'm not quite there. Let's just say I randomly sample, get 10 values. If I'd like to describe this data, that's called descriptive statistics. So you can describe it with values. Little x bar for us is the mean of a sample. Little x tilde is the median value, the middle value when you line them all up. Little s is the standard deviation. There's lots of measures you can find with a set of data. R is the range, the max minus the min. So we can also do graphics, right? I could maybe make a histogram and say whose GPA, how many are between 1 and I don't know, maybe 1.5, 1.5 to 2, 2 to 2.5, right? And then you've probably seen histograms look like, kind of look like these bar graphs, right, that show how many are in each category. So there's lots of ways to display data as well. Many types of graph, and there's a nice statistical package. You'll see it down. You probably see it in my window mini tab. We'll use that in a little bit. The kind of statistics that we're going to talk about for our application is inferential statistics. You collect a set of data and you try to infer something from the sample about your population. So first of all, a sample is just a subset of the population. So imagine this is the whole population. We could just say Rose-Hulman students could be our entire population. And I want to take a nice random sample. That could be stratified sampling, systematic sampling. There's a lot of ways to take samples, but you want to make sure it is random. So let's say we take, again, before I took 10 students. No. No. And then this is my sample, and then from that sample, let's say that the sample I had above, if I average those 10 GPAs, let's say I had gotten 3.17. Now this is only a random sample of 10, but how well does this represent the mean of the population? So all quarter we've been working with populations and population distributions. You've seen the Greek letters, mu, sigma, I don't know what else we used, well, alpha, beta, anything that's Greek represents the population, but this is just the mean we got for the sample. Mu would be the mean for the population. So is this a very representative value of the mean of the entire population of students? If I took every single student at Rose, there's about, I think there's about 2,000 now. And let's say I averaged all 2,000 GPAs divided by 2,000. Is 3.17 a good indicator of what the true mu is? I mean, we could find mu if we could talk to the registrar and they give us every single GPA, but probably the best we can do is get a random sample and then try to infer how close to the true mu we are. So one value alone doesn't do a very good job at representing an entire population. And again, with a population, you're usually looking at parameters. I always say, like, what's the parameter for the exponential? You're talking about a population value. Sample statistics are usually given by, I want to say, alphabetical letters, not mu and sigma. And populations are given by the Greek letters. A sample mean x bar can be quite different from the population mean mu. So we had gotten for 10 randomly chosen students the GPA of Rose to be 3.7, but mu, I mean, maybe mu is, I'm just gonna make up a number, 3.35. I mean, I don't, there's some question about how good this is. This is only a sample of size 10. Of course, if you take a bigger sample, we could get closer to the true mu, but there's some probability involved with how good this is. So instead of just giving you a single number, what's a little bit better than to give more precision is to build actually a confidence interval. So maybe instead I have an interval that says I'm 95% sure that the true mean GP at Rose is somewhere between 2.8 and 3.25. Again, I don't have just one number, but now I feel a little bit like this is more reliable. Again, didn't tell you how I built it, but right now I'm just saying I'm 95% certain that this interval contains the true mean mu. And that's what I'm trying to do with that confidence interval. I'm trying to give some confidence to this interval of numbers that I hope contains the true parameter of interest I'm looking for. So this is what we call a confidence interval. And the main thing about getting it is we need a random sample. And in this class, I'm just going to build one for mu right now. We can build a confidence interval for any parameter you want. We could build one for sigma, the standard deviation of GPAs. Anything, the true median of GPAs. I mean, you can build a confidence interval for any parameter you want. And the confidence level tells you the degree of reliability of the interval. So of course a 95, I'm more confident with this than a 90%. But the thing is, with a 90%, we can actually get a tighter interval. So maybe now this is 2.9 to 3.21. I mean, yes, I've lost some confidence, but I've gained a little tighter interval. So, I mean, I always joke too, I mean, we could have a 100% confidence interval. I'm 100% confident that the true mean GP of Rose-Hulman students is between 0 and 4.0. I mean, that's a useless statement, but I'm 100% confident in that interval. So I wanted to go to Minitab and build a couple confidence intervals for you so you get the gist of how I'm making them. And then we'll do some problems, but I think I'll just stay with a short video for now.